Okay, let's dive into this fascinating 4,000-year-old mathematical puzzle and uncover the magic cheat code that unlocks quadratic equations. Welcome to this explainer. If you've ever studied algebra, there is literally nothing quite as frustrating as hitting a brick wall in a problem where the numbers just stop making sense. Today, we're taking a seemingly dry algebraic formula and revealing the incredible global history and the hidden geometry right behind it. We're talking about the mystery of the missing roots. So if you've ever stared at a quadratic equation and wondered what it actually means, beyond just pushing letters around a page, well, you're exactly in the right place. We usually solve quadratic equations to find exactly where they hit zero, right? If you've ever graphed one of these, you know the drill. You're looking for those specific points where that U-shaped curve, or parabola, cleanly crosses the horizontal x-axis. But what happens when you get that one rebel parabola that just floats up there in the sky, completely avoiding the line? I mean, did you break the math? Did the solutions just vanish into thin air? Are they fundamentally broken? Well, for centuries, some of the most brilliant mathematical minds in history thought exactly that. Today, we're going to track down exactly where those missing roots are hiding. Section 1. The Magic Discriminant. So, to solve this mystery without doing all the hard, tedious math every single time, we use a very special time-saving tool. Instead of grinding through the entire massive quadratic formula, we can use what's essentially a math X-ray machine. It's this tiny, specific fragment of the formula, b squared minus 4ac, and it's known as the discriminant, often represented by the Greek letter delta. Without calculating the whole equation, this little piece looks right inside the math and instantly diagnoses the fundamental nature of our roots. It basically gives you an immediate sneak peek at exactly what kind of answers you're about to get, which saves you an absolute ton of time and frustration. Section 2. Visualizing the roots. Let's see how this tiny formula builds a direct bridge between abstract algebra and the actual physical shapes we see on a graph. The crucial point here is that just by checking if delta is positive, 0, or negative, we know exactly how our parabola behaves in the physical world. If your discriminant is greater than 0, boom, you have two distinct real roots. That means your parabola decisively crosses the x-axis twice. If the discriminant is exactly 0, the curve just skims the axis, touching it perfectly once, giving you a single, real, repeated root. But what if it's less than 0? Well, there's our floating parabola. It never touches the x-axis at all, meaning there are absolutely no real roots to be found. And the power of the discriminant doesn't even stop there. If delta is positive, we can actually predict whether our roots will be clean, rational numbers or messy, irrational decimals, just by checking if that delta is a perfect square. Think about it. If your discriminant is a perfect square, like 16, the square root of that is just 4. You get nice, neat, rational roots, like clean integers or simple fractions. But what if your discriminant is, say, 32? You can't get a clean square root of 32, so you're stuck with irrational roots, those infinite, messy decimals or surds that just go on forever. It is genuinely wild how much predictive power is densely packed into just b squared minus 4ac. Section 3. The Imaginary Number Realm. Let's jump back to that negative delta for a second. The floating parabola that never touches the axes? If you try to plug a negative discriminant into a square root, it totally breaks the standard known laws of mathematics. It's mathematically scandalous. Think about the fundamental rules we all learned. A positive times a positive is a positive, right? But a negative times a negative is also a positive. So taking the square root of a negative number was considered completely, totally impossible for hundreds of years. When ancient mathematicians would hit a negative discriminant, they would literally throw up their hands, declare the problem definitively unsolvable, and just walk away. And this brilliantly illustrates the exact moment where mathematicians had to bend the rules and invent imaginary numbers. They defined the letter I as the square root of -1, which means I squared equals -1. Now, on the surface, making up a new mathematical rule just to solve a problem kind of sounds like a middle schooler trying to cheat on a math test, right? But in this case, defining this single, completely radical new rule unlocked an entirely new dimension of mathematics. It literally paved the way for things like quantum mechanics, electrical engineering, and modern physics. So when delta is negative, the roots absolutely still exist. They aren't gone. They just live in what we call the complex plane, which beautifully combines real and imaginary numbers. Your answer might look something like 2 plus 5i. These are known as complex numbers, merging a standard real part with this new imaginary part. So our floating parabola isn't broken, and it definitely isn't rootless. Its roots are just perfectly preserved in the separate, non-real dimension. It is such an elegant solution to a problem that completely stumped humanity for generations. Section 4. A 4,000-year math journey. Humanity struggled for centuries to figure out the exact same algebraic concepts you're learning today. You aren't just memorizing static formulas. You're standing on the shoulders of ancient giants. We're actually tracing an epic global detective story that spans 4 millennia. It starts in the blistering deserts of ancient Babylon, almost 4,000 years ago, passes to the geometric masters of ancient Greece, travels over to the brilliant minds of India, flourishes through the Islamic Golden Age, and finally crystallizes in Renaissance Europe. Each culture passed the baton across empires and centuries, adding their own unique genius to the puzzle of the quadratic equation.
The crazy thing is, the ancient Babylonians didn't even have the algebra we recognize today. Instead, they used literal verbal recipes for finding areas that perfectly mirror what we now call completing the square. Just imagine trying to solve a complex quadratic equation without actually having the letters x or y, and you're chiseling the whole thing into literal mud as a word problem on a clay tablet. And because they worked strictly with physical, real-world lengths and agricultural areas, it meant they only ever looked for positive solutions. I mean, you can't exactly have a negative field of crops, right? The contrast between ancient cultures here is just fascinating. While the Greeks were restricted by drawing physical, geometric shapes for positive answers, Indian mathematicians like Brahmagupta took a massive paradigm leap forward. They started using abstract symbols and, crucially, actually accepted negative numbers as valid solutions. Why? Well, because their mathematics was deeply tied to concepts of financial debt. That allowed them to conceptualize negative values in a way that physical geometry just couldn't do. By the 12th century, another Indian mathematician, Bhaskara II, provided the very first clear explanation of the discriminant concept itself, detailing how it fundamentally determines the nature of an equation's solutions.
Section 5. The Symbolic Mathematical Revolution.
So let's jump ahead to the Renaissance. This is where the math we recognize today truly takes shape. For thousands of years, abstract algebra and visual geometry were treated as completely separate subjects. They simply did not mix. But René Descartes changed the world by finally connecting the two. He created the coordinate plane, the literal x and y axes grid that we use every single day, which allowed us to visually map the discriminant. Descartes' absolute genius was that he finally allowed us to actually see the math. He literally showed us the floating parabola. But even brilliant historical minds had their blind spots. Initially, the concept of the square root of negative numbers was vehemently rejected. In fact, René Descartes actually coined the term imaginary as a literal insult. Yeah, he thought these numbers were completely useless, nonsensical garbage. It took centuries for mathematical legends like Gauss to step in and finally prove that complex numbers were absolutely essential to completing the puzzle. Gauss showed the world that these so-called garbage numbers weren't just glitches, but a fundamental part of the universe's logic.
Section 6. Putting it all together.
Okay, let's tie our magical cheat code and this incredibly rich human history all together. By simply calculating the discriminant, b squared minus 4ac, you are utilizing a tool forged by the Babylonians, Greeks, Indians, and Europeans to instantly reveal the hidden nature of any quadratic equation. Just by checking that tiny fragment, you immediately know if your graph crosses the line twice, touches it perfectly once, or floats off into the complex plane. You aren't just doing math here. You are holding 4,000 years of human genius and global collaboration in a single, brilliantly simple calculation. Algebra is not just a static set of rules to memorize. It's a living, breathing human adventure that you are now a part of. So, the next time you calculate a discriminant and get a negative number, don't think you broke the math. Don't see it as a dead end. Instead, ask yourself, what other invisible dimensions of our universe are just waiting for a new set of rules to be discovered? Keep exploring, keep questioning, and I'll see you in the next explainer.